Lagrange multipliers for Calc 1. Lagrange multipliers theorem, Calculus 1 version. Assume that f of x and y and g of x and y have partial derivative functions, and those partial functions are elementary functions. If f has a local extremum on the constraint curve, g of x and y equal to c at a and b, and if the two partials, partial of g with respect to x at a and b and partial of g with respect to y at a and b are not simultaneously zero, then there exists a scalar lambda such that partial of f with respect to x at a and b is equal to lambda partial of g with respect to x at a and b, and partial of f with respect to y at a and b is equal to partial of g with respect to y at a and b. To prove this theorem, let's start by the assumption that we're optimizing the function f of x and y subject to the constraint g of x and y equal to c. Since x and y are related by the implicit constraint equation g of x and y equal to c, we are effectively optimizing f of x and y of x, where y of x is the implicit function of x defined by this implicit constraint g of x and y equal to c. So the critical point occurs when the derivative with respect to x of f of x and y of x is equal to 0. But what is this derivative? Because y is a function of x, we can define this implicitly by partial of f with respect to y times derivative of y with respect to x plus partial of f with respect to x. And we set this equal to 0. Then we're going to solve for dy dx, which is going to give us negative numerator partial of f with respect to x, denominator partial of f with respect to y. This implies that at any critical point, a and y of a, or a and b, the derivative of y with respect to x at that point is going to be equal to this quotient, which is partial of f with respect to x over partial of f with respect to y times a negative sign, evaluated at the point a and y of a. On the other hand, differentiating the constraint equation g of x and y equal to c implicitly gives partial of g with respect to x plus partial of g with respect to y times dy dx. Again, we're assuming y is an implicit function of x. And it has to be 0 when we're evaluating at a critical point. Now, solving for dy dx from this derivative gives us dy dx is equal to negative numerator partial of g with respect to x, denominator partial of g with respect to y. Again, since a and y of a is a solution, we're going to have that dy dx evaluated at a and y of a is equal to negative partial of f with respect to x divided by partial of f with respect to y evaluated at a and y of a. So now we have this side of the equation, the left side of the equation here also happened in the previous equation right there. Therefore, we can set the right side of the equations equal to each other. That is, the negative partial of f with respect to x over partial of f with respect to y is equal to negative partial of g with respect to x, partial of g with respect to y, evaluated at the critical point a and y of a. We said this, or we defined this quotient to be equal to lambda. Therefore, the system partial of f with respect to x equal to lambda partial of g with respect to x, and partial of f with respect to y equal to lambda partial of g with respect to y at the critical point is satisfied. And we can use this system to find the critical point where f has critical points on the constraint implicit curve g of x and y equal to c. Consider z equal to f of x and y subject to constraint g of x and y equal to k, where k is a constant. Suppose that f has local extremum at p equal to point a and b. Here we shown a few level curves for the function z equal to f of x and y. You can see the f of x and y equal to 5, 6, 7, and 8. And you can see that p is located on the level curve f of x and y equal to 7, meaning that the function f at point p uh, is equal to 7. You can also see that p is on the constraint curve c, which is also g of x and y equal to k. You can see that the constraint g of x and y equal to k, or the curve c, is tangential to the level curve f of x and y equal to m, or maximum. In this case, m is 7. And this is why, because the constraint curve is not going to cross the level curve and move on to higher values, because the maximum is at p. If it crosses the level curve, it's going to get bigger than the value 7, and so it has to be tangential. So what's the significance of that? Now, the two curves being tangent to each other at a and b means that their tangent slopes are at a and b are equal. Uh, and so that means that the derivative of y with respect to x at a and b is going to be the same for both functions. One is that negative partial of f with respect to x over partial of f with respect to y at a and b, and the other one is the negative partial of g with respect to x over partial of g with respect to y at a and b. So this is another way of imagining what the Lagrange multiplier theorem does.